Welcome back to our lesson practice review, where we have our final lesson in chapter 2, lesson 11. And this one here is still focusing on our imaginary numbers or our complex expressions. But it kind of adds in this idea we've mentioned before, but we've mentioned kind of two key terms here. The first one is conjugates, like this. It's when we have kind of two binomials here that are the same values, but one is addition and one is subtraction. What ends up happening here is we kind of see as we go through and we multiply two conjugates together, we end up getting this situation where those inside terms end up going away because they add together and subtract and become nothing. And therefore, we get what we call as a difference of squares. But in this situation here, like 9 and negative 16i squared, what's special about it with complex expressions is that negative 16i squared now just becomes an integer because we do I squared, which becomes negative 1, which then becomes 9 plus 16, which gives us just a value. And so we're kind of combining an old term here where we are kind of taking what we know about conjugates, also difference of squares, and then kind of applying some of that knowledge to what we know about imaginary numbers and complex expressions. So, complete each area diagram puzzle for number 1 and 2. The first one here, since it's 5 minus I, we know that this outside number has to be that's not right, positive I here. And then we would get I times negative I, which is negative I squared, which is also equal to positive 1. For number 2, negative 8 has to be negative 8 here to get positive 64. And then negative 8 was that times 11i. And then it has to be a negative 11i since the two negatives become positive. And then the bottom right one, the positive and negative, would become negative 121i squared. The I squared and the negative cancel out to just give us 121. So it looks like negative 8 and negative 11i. Problems 3 through 5. Write an expression that, when multiplied by the given expression, has a product of only real parts. So again, on this one here, the idea here is that we're going to be using what we call the conjugate, which in this case would be 13 plus 5i. And then just, I don't know, we'll do this for the first time. We won't do it for every single time, but if I just do 13 minus 5i and 13 plus 5i here, we get 169. 13 times 5 is 65i. We get positive 65i. Then we get negative 25i squared. So what you notice here is that positive 65 and negative 65 cancel out. Negative 25i squared becomes positive 25. And then that will give us a product of only real values because all my i's have now gone away. So if we know what we know about conjugates, I'm not going to necessarily multiply that out again. Now I'm just subtracting 19i instead of adding it. And then for number 5 here, again, I'm keeping everything the same, except I'm changing the sign in between. Instead of subtracting, I'm going to add 7i. And again, if you need the practice to double check and make sure, you're actually going to multiply that out to see that those inside values or those I values end up canceling out. For number 6, match each quadratic function with its zeros. So in these ones here, we're using what we know about the zero product property and setting each of them equal to 0. So on this one here, I'll probably do this to the side. I might need some more space here. So x minus 16i equals 0. I'm just going to add 16i to both sides. Same thing here, x plus 16i equals 0. Subtract 16i from both sides. And so first one here goes in that third spot. Then we got 3x plus 5i equals 0. I subtract 5i. Then I divide by 3 and I negative 5/3 I. Again, I could do the other one, but I can kind of see here that we only have one that has negative 5/3 I as a answer. And what you'll notice also is that each of these here that I'm solving for, the solutions are just going to be the opposite value, right? One of them will be positive and one of them will be negative. So I'm really only solving one of these at a time here for x minus I equals 0. I add I to both sides, I divide by 4, and I get I over 4, which is the same thing as 1/4 I, which is here. And last but not least, 2x plus 4i equals 0. I subtract 4i from both sides. I divide both sides by 2, which gives me negative 2i, which C, D, A, B. Okay, for number 7, select all the functions that have zeros of 2i and negative 2i. So in this one here, same idea. We're going to kind of have to solve these here. The way we solve them is that we're really just setting the y value equal to 0. That's what it means to have a 0 here. So all of these end up becoming 0, and I'm just going to kind of solve them. So 0 equals x squared plus 4. I subtract 4 from both sides. I take the square root of both sides. The square root of negative 4 ends up giving me plus or minus 2i. And so A is good. For B here, we're going to do 25x squared plus 100 equals 0. Subtract both sides by 100. Divide both sides by 25. Take the square root and get x equals plus or minus 2i again. So B also works. I wonder if all of them will be an answer. That would be kind of interesting. So next one, 9x squared plus 16 equals 0. Subtract by 16, divide by 9, and this doesn't divide equally, so that when I take the square root, I'm not going to necessarily, I guess I'll go ahead and do this to get the answer, but we end up getting plus or minus root, so 4/3 I, because the square root of 16 is 4, and the square root of 9 is 3, and this negative here becomes I, so this one does not work. Next up, we got D here, which, again, running out of room, sorry about that. 9x squared plus 36 equals 0. Subtract 36 from both sides. Divide by 9. And we see when we take the square root, plus or minus 2i. So D also works. And last but not least, 4x squared plus 25 equals 0. Subtract 25 from both sides. Divide by 4. Take the square root of both sides to get plus or minus 5 halves squared. So this one doesn't work either. So our answers for 7, A, B, and D. Problems 8 through 9. We have a function f of x here equals 9x squared plus 49. So I may have to go ahead and do this one in one way and then kind of come back to change this up, because this one here, when I look at this, first of all, there's no greatest common factor. It's not a difference of squares because it's not subtraction. I can figure out the answer because I know the stuff about i's here, but I want to show you one method here to help out if you need it, so that we can kind of have our two solutions here, kind of, going backwards from what we did from number 7. Is that I can find my two zeros here by setting it equal to 0 and then solving. So subtracting 49 from both sides, dividing by 9, and then taking the square root to get plus or minus, and then that's 7 over 3i. So I get these two solutions, x equals positive 7/3 I and x equals negative 7/3 I. And again, a way to kind of backwards work through this is like multiplying the 3 to the left side. 7i, 3x equals negative 7i. And then moving the 7i over. So in this case, subtracting, and this one adding. So I get 3x minus 7i and 3x plus 7i. So that's a way to kind of get the two factors here, to get 3x minus 7i times 3x plus 7i. I'm not sure if we should have gone over a different way of kind of going through this, but that is one way definitely to get the two factors. All right, for number 9, which of these features does the function have? So in this one here, it does have zeros. Again, I kind of already went through this, which is why I'm assuming I did it the wrong method. But which of these features does the function have? It does have zeros. We found 2 of them right here. It does not have x-intercepts because these zeros are i's. They have i's. And so they are imaginary answers or imaginary solutions, which means that we don't actually cross the x-intercept. All right, for number 10, write an expression when multiplied by -8 minus 5i has a product with only imaginary parts. So this one's a little bit different, where we actually want our whole numbers or our real numbers to cancel out here. And so when I'm going through this, I'm going to want to make sure that, let's talk about the box here to kind of show. So we have -8 minus 5i, and this bottom right one or bottom left one is going to be I also. We want, these two numbers to be the same. And so what that means is that this has to be 8. So I multiply it by 5 to get -40. And then this has to be 5 to get -40 as well. Because then when these two add together, -40 and then -40i squared, they will end up canceling each other out. So in this one here, we end up getting an answer of 5 plus 8i. So notice the pattern here, what happens, right? Same numbers, reverse signs, and then reverse positions. Which one is the real part and which one's the imaginary? For number 11, multiply these two things to show that it's equivalent to this part right here. So again, trusty box here, ax, bi, ax, -bi. We got a squared x squared. We have negative abxi, yuck, and then positive axbi. Luckily, these two things are opposites. And when we add them together, they go away. And then I get negative bi squared. And then the I squared just becomes -1, which makes this just b. So when I add everything together, I end up getting what I thought was equivalent to. Spiral review. Problems 12 and 13. Determine if the function has 1, 2, or no x-intercepts. If the function has x-intercepts, what are they? I'm going to go ahead and actually kind of solve these out. So plugging in 0 for y and see. I'm going to go through, since I have to find the x-intercepts anyways, I'm going to go ahead and kind of try to solve this. So subtract 4 from both sides. Divide both sides by -1. Take the square root of both sides. This is where I get plus or minus 2. Subtract 11 from both sides. So I got -11 plus or minus 2 equals x. So my two solutions are -11 plus 2, -11 minus 2, which means that I get -9 and -13. So the x-intercepts are -9, 0 and -13, 0. So 2 x-intercepts and at -9, 0 and -13, 0. For number 13, 0 equals -x minus 9 squared minus 5. Add 5 to both sides. Divide both sides by -1. And then when I try to take the square root, I end up getting the square root of a negative number, which means that I don't have any x-intercepts. That wraps up our final lesson practice for chapter 2. If you're going to continue on with the videos, it will move on to chapter 3 here, where we kind of exit our quadratic section. So good luck and hope to see you in the next one.